Hello and welcome back. Let's take a break from basis and let's talk about the method of least squares. So sometimes we have systems of equations that we can't solve without parameters. But the thing is, we can approximately solve them. So let's take a look at an example. Let's say that we got some experimental data. Say this happened maybe in a physics lab or a chemistry lab, and we got some data, and we know that it should be linear, but it's not quite. Well, let's just plot our data first. So our first point was 1, 1. Our second point is 2, 3. And our third point is 3, 2. Now, just by looking at this, we can see, this isn't quite linear. If we try to draw a line, let's draw a line in red first, and then we'll draw a line in orange, and we'll draw a line in green maybe. Well, we can draw a line going through these 2 points. Now it's not going to touch that point. We can draw a line going through these 2 points. It's not going to touch that line, or that point. And finally, we can draw a line going through these 2 points, but it's definitely not going to touch that dot. So how can we draw a line, I'll draw this line in black, that approximately solves and comes as close as possible to all 3 of those points? Well, this is where method of least squares comes in. So if we put our points ty over here, we're going to get our first point, which is 1, 1. We're going to get our second point, which is 2, 3. And we're going to get our third point, which is 3, 2. And we want a linear line, so we can call this y equals x1 plus x2t. Right, or y equals mx plus b from regular graphing. But we want to write it in terms that we know from linear algebra. So let's write our points in. Well, we're going to get, let me just make this a little quicker. I already have this done. We're going to get 1 equals x1 plus x2. We're going to get 3 equals x1 plus 2x2, and we're going to get 2 equals x1 plus 3x3, x2, sorry. I don't know why I wrote x3 now. There's no x3. If there's an x3, we could solve this. So let's just put this into a matrix form. Let's put it into the form ax equals b. This is our b, and this is ax. So our a is going to be 1, 1, 1, 1, 2, 3, and we only have x1 and x2, and this has to equal 1, 3, 2. Well, if we solve this, we're going to get that we have a parameter, and well, we simply can't solve this to an exact point. But we can solve it using this formula. Now we know that ax equals b is our regular way to solve something. But what if we times both sides by A transposed so that we get a 2 by 2 matrix here and we get a 1 by 2 matrix over here? Well, we can do what we want. We can see if it works. Spoiler alert, it's going to work. So our new formula is this. Now, if you forgot how to transpose, don't worry. There's a video on that. But what we're going to do is we're going to times A transposed, which is just the matrix if you basically flip it, by A. We're going to leave our x, and then we're going to times A transpose by B. What we're going to end up with is this. 3, 6, 6, 14. x1, x2 equals 6, 13. Okay, nice. Now we have a system that we definitely can solve. Well, if we use Gauss-Jordan elimination, we get this. This tells us x1 equals 1 and x2 equals 1 over 2. So our line of best fit is y equals x1 plus x2t, remember? So y equals x1, which is 1, plus our x2, 1 over 2t. Which looks a lot like this. It starts right here at the 1, and it goes up by half each time, so yeah, it's actually a pretty good sketch. But that is our line of best fit. Maybe I should take away this point here so that you don't get it mixed up with any of the points. And of course, it doesn't touch any of the points, but it comes as close as it can to touching the other points. So this is a very powerful tool that we can use when we're working with experimental data that will never be perfect. So thanks for watching this video. I hope it helped you. I hope you can use it later on in your studies as well, because this is a very powerful tool, as I've said many times. And I hope to catch you in the next video, where we're going to talk about something very crazy, but very fun.